What we've talked about so far is the generalization of the Hooke's law that we had been employing in ME 231 towards the incorporation of multi-axial stress states, in other words, towards the generalized Hooke's law. In the case of isotropy. So that, in some sense, at least for isotropic materials, it takes full account of the complexity of mechanical loading. But that's not the only type of loading we can have on materials. It turns out that the materials respond not only to the loads that you apply to them, but also to the amount of energy that you can apply to them, in particular towards temperature changes. So we want to talk about also so-called thermal strains. And the starting point for the discussion is, for most of them, as is the case for most discussions, it's a simple experiment. And what we're going to do is we're going to take a rod. So the rod itself, of course, it lies in 3D, but we are doing the experimental measurement to concentrate only in one dimension along the axis of the rod. And the rod, we're going to call it stress-free. So all the surfaces are stress-free. So there is no load applied to it. In other words, if we were concentrating on our standard setting of a pure mechanical load, then we don't expect to see any strains. And this rod has some initial length L. And it is at an initial temperature, which we are going to call T0. So T is going to indicate the temperature from now on, and T0 is the initial temperature. The initial temperature, for instance, could be the temperature of the medium that this rod is in equilibrium with from a thermodynamics perspective, but ultimately it will serve us just to calculate temperature changes. In other words, when the temperature eventually will change from an initial value towards some final value. So T would be the current value. So that's the current temperature. And from these I can calculate or define that delta T is equal to T minus T0. That is our temperature change. It can be positive or negative depending on whether the temperature is increasing or decreasing. Okay, so that's our initial or our reference temperature, and T is our current temperature. And now what we do is we do an experiment where we have this rod, which is stress-free, at an initial temperature T0, and what we do is we change the temperature. And as a result of that, what we typically observe in an experiment is that the rod elongates. So you get apparently a positive strain, and that is associated with the length change delta L that is induced by the temperature change. And now from an experimentalist point of view, I would like to have a rigorous characterization of the factors which influence this temperature change. So we go ahead and do experiments. And so the thermal expansion is going to be monitored as a function of the variables that possibly control it. So first of all, we can easily observe that if we take a length that is twice, then this thing is going to be twice larger. Half the length is going to be half as large. Okay, so in other words, delta L ultimately is proportional to the original length L of the beam. Then we also observe that if we say double the temperature change, which in this picture is assumed to be positive along with another parameter that we're going to eventually talk about, but if delta T is doubled, then we see that delta L is doubled. Okay, so we see that ultimately that delta L is proportional to delta T as well. And of course, what we will see is that if delta t is positive, delta L is positive as a consequence of proportionality. If delta t is negative, then delta L is also negative. So if you cool down the beam, it will contract instead of expand. So finally, we see that this trend is observed for any material that you could possibly make the beam out of. However, for a given temperature change and initial length, for every material, the amount of elongation is different, okay? And therefore, to make the observation, the proportionality inequality, what we do is we go ahead, insert a material parameter, alpha, which allows us to conclude something about the amount of thermal expansion. So in this particular case, of course, what I could do is I could divide both sides by L, and I could see that the amount of strain, be careful, it's a stress-free scenario, the amount of strain is equal to alpha delta T. Okay, so we get a so-called thermal strain due to the fact that the temperature is changing and we have a strain despite the fact that there is no actually loading on the structure. So here, alpha is called the coefficient of linear thermal expansion. Now, you'll notice that I put the word linear in parentheses. Often, this is not mentioned. One simply says the coefficient of thermal expansion, but what is really meant is the coefficient of linear thermal expansion. Now, as soon as we see this additional adjective, you might suspect that there is another type of coefficient of thermal expansion. I'm going to mention that shortly. What's a good idea to keep in mind, as we had done before for the Young's modulus and the Poisson ratio, is the range of values that you could possibly observe for the coefficient of thermal expansion. And these values are values that typically lie, for most metals at least, in the range of 1 to 10, 10 to the minus 6. Okay? And the other thing, of course, is what is the coefficient of linear thermal coefficient of thermal expansion? What are its units? Well, the units, the dimensions of alpha is, well, this is dimensionless, so it's going to be 1 over temperature change. And we can assess temperature change either in terms of degrees Celsius or in terms of 1 over Kelvin. Kelvin is just as good as degrees Celsius in terms of measuring temperature change. So either one is fine. You have 1 over temperature as the units, and the magnitude is seemingly small. It's very small, but remember, eventually the temperature changes could be significant, could be of the order of several hundred degrees Celsius, and as a result of that, you could get appreciable strains. And the question is, so what? Well, we're going to see the so what part very soon. Now, a quick remark. The coefficient of linear thermal expansion is indicated to be a value that is positive. Does it have to be positive? So in other words, when I heat something, does it necessarily have to expand? So in other words, is it possible that I heat something and it actually contracts? That might seem unnatural to you at first, but that is exactly the situation we face with the Poisson ratio. It also looks unnatural at first, but it is entirely possible. Turns out that you can also have a coefficient of thermal expansion that actually is negative. So in other words, you heat the material up, it contracts, or you cool it down and it expands. And those materials you don't find widely in nature, but just like for the case of the Poisson ratio, you can engineer them. All right, so well, this is our observation. And now we go ahead and try to expand that intrinsically 1D scenario to a 3D scenario. And in 3D, what we're going to do is we're going to imagine our simplest experimental setup, which is a block. And we have now our coordinate directions x, y, and z. So we have the length, the width, and the height. And what we do is we take this block. Initially it is at some reference temperature T0, and then we heat it up. So then we observe that the length change along each direction likewise is proportional to the original length, proportional to temperature change, and it's just to make the equality, to make the proportionality and equality, all we have to do is insert a constant, a material parameter, in this case again alpha, delta TL, and then we monitor that for the other direction we also have a similar proportionality, and in principle you could have different coefficients of thermal expansion in each direction, but let us omit that for a second and insert the same value. So let me correct this. It should be the corresponding dimension. So now, as a result of that, what we obtain is that the strain along the x direction, despite the fact that we have again a stress-free scenario, despite the fact that we have no loading, we get a strain along the x direction, which is alpha delta t, a strain along the y direction, which is also alpha delta t, and a strain in the z direction, which is alpha delta t. And in all cases, importantly, I do not see a distortion in the shape of this cube. In other words, these angles don't change, only the lengths of this cube or parallel piped, they just changed. So in other words, you don't get any shear. I'm just going to write gamma 0 so you can put the appropriate choice of indices in there. So there is no shear. And so what we're saying is we take a material, and first of all, we are imposing a temperature change, and we see that we get exactly the same amount of strain for a given temperature change along every direction. So in other words, the material parameter that governs that expansion is the same for every direction. There is directional insensitivity, and that is an indication of isotropy. So we have to keep that in mind. Okay. The isotropy assumption comes back again. And it turns out that if the material is isotropic, and if you change the temperature, you don't get shape distortion. You don't get any shear strain for the case of isotropy. So this observation goes along with that. So it turns out, therefore, you might suspect that if the material is an isotropic one, you will in general have different amounts of strains along every direction for a given temperature change. So these will be different factors, alpha x, alpha y, alpha z, for instance. And moreover, what you will observe is that the shape of the angles, which are initially pi over 2 in this simple example, they might increase or decrease depending on the coefficients that govern it. In other words, you will get shear strains for an anisotropic material even without any mechanical loading, just due to the fact that you are changing the temperature. Okay, but here we're concentrating on isotropy, but it's important to keep in mind the underlying assumptions that we are making in this case regarding the nature of material behavior. So from these three quantities, you can immediately see that in this particular example, we get a strain, a volumetric strain in this case. Remember its definition. The volumetric strain is equal to the sum of the normal strains, which are all the same in alpha delta t, which comes out to be 3 alpha delta t in this particular scenario. So the ratio of the change of the volume with respect to the initial volume is 3 times the coefficient of linear thermal expansion times delta t, and this quantity is sometimes called let's indicate it as alpha V, although we're not going to use it, the coefficient of volumetric thermal expansion. Okay. So we have to be careful whenever we try to extract the values of the material parameters from a database for material parameters, because sometimes what you will see is just the material parameter indicated as coefficient of thermal expansion, and you have to make sure that if it's not indicated, it's actually the linear one and not the volumetric one. Sometimes there is a distinction, but one is just a factor of 3 with respect to the other, so it's easy to know one if you can determine or find the value of the other one. All right, good. So now we have an idea, an experimental characterization that gives us an idea about what to do, and we can extend that idea to a 3D experimental setting and rigorously write down a relation for the strains that we are observing. But that was for the case where we were not imposing any mechanical load on the structure and only a thermal load, let me say. And now what if we have both of them? Well, if we have both of them, you can imagine that, one, we are dealing with small deformations, and two, these are all reversible or in some sense elastic deformations. So in other words, if I remove this temperature change, if delta T increases and then decreases, all the strains will go back to zero. By the way, these relations are defined. So just like sigma equals E epsilon in a symbol 1D scenario, you put a load, you get a strain, you remove the load, the strain goes back to zero. You increase the temperature, you get a strain, you remove the temperature change, in other words, you decrease it back again, and you remove that strain. So everything is reversible, so we have in some sense linear elasticity still, and in that range, the principle of superposition applies. So that will lead us to the concept of directly or an expression, an explicit expression for the form of generalized Hooke's law. With temperature change. Okay? And this is sometimes called not linear elasticity, but linear thermoelasticity, because you have both mechanical and thermal loads, but those loads induce only elastic deformations, and those deformations are small. So, well, how does the principle of superposition going to work? Because it seems that we have a problem that's governed by small elastic deformations. I can certainly apply it. Well, the way it will apply is, first I think about the strains, and I think about the case when I would have only mechanical loading. If I have only mechanical loading, I know what to do. Epsilon x is 1 over E, stress in the corresponding direction minus nu, the remaining two stresses, and likewise for the other two strain components. That's the case if we have pure mechanical loading. And now, on the other hand, if we had pure thermal loading, then I just determined experimentally what we're supposed to do. We just get a strain that is equal to alpha delta T in all directions. And the question now is, well, what happens if I have both of them at the same time? Well, you just need to go ahead and apply the principle of superposition, individual solutions to two problems. And now if you have a new problem that is the sum of the conditions in the two problems, the solution is the sum of the solutions. Okay, so the superposition principle applies. So this is a very powerful principle that we have already used once before in deducing the form of the generalized Hooke's law, and we're going to use it again in the future. All right, good. Good. So, well, let's recall what happens in the case of shear strains. Well, for shear strains, I already know that the relations are somewhat simpler. We have the expressions that relate a given shear strain to a given shear stress. And now, moreover, we know from our experimental observations that there is not going to be any thermal strain contribution to shear strains. Okay, so those are the shear strains still. And therefore, this is now our generalized Hooke's law with temperature change. Okay, and here, what you can also do as a side exercise now is to verify that if you sum the left-hand sides, you would get the volumetric strain. And if you, on the right-hand side, you will get, we've done this before, it is 1 over the bulk modulus multiplying the hydrostatic stress. That is equivalent to the summation of the blue terms. And if I sum these, I will get 3 times alpha delta T, or in other words, the coefficient of volumetric thermal expansion multiplying delta T. Okay? So on this side, we have this simple expression that relates temperature changes and hydrostatic stresses to the volumetric strain. Well, let's emphasize a few things here that are important. So, first of all, what we see is that if the thermal strain is equal to 0, then it doesn't mean that you have zero stress, or not, it doesn't mean that you have zero loading. That loading could be, we're only talking about normal strains, that loading could be a bending moment or an axial load. So if this is 0, it doesn't mean that the stress, or therefore the load, is 0. It means that the sum of the blue and the red contributions is equal to 0, right? So, in particular, if you have a structure that is constrained from expansion along its normal directions, then, well, if you heat up the material, and if alpha is positive, you will certainly end up having stresses, because if this is 0, and if this is non-zero, then there must be some terms here that balance that contribution to end up with a 0 value. So at this point, you should discard the strong notion that is embedded in your minds, at least in the context of linear thermal elasticity, that if you have 0 strain, you have 0 stress. Or conversely, the second point is, if you have 0 stress, doesn't mean that you get 0 strain. And we've already observed that, because if you change the temperature despite the fact that you have 0 stress, then you can still get a certain amount of strain. So in other words, this is a relation that is always going to work. And from now on, right, so 1, what we've done is sigma is not anymore E times epsilon. There are other contributions here. And 2, sigma is not E epsilon even in 1D, because there could be a temperature change which induces a certain amount of strain as well. So those are the things that we need to keep in mind, and if we do so carefully, then we can solve problems that we couldn't have done so before. Okay, so let's go ahead and apply this these concepts to a simple example.